So you see, there's a very deep problem in string theory that it cannot harbor an accelerating solution in a very simple way.
I see.
So, so we gave up this idea that it is possible. And around the same time, papers came which says that can string theory have a deSitter minima? The answer was no, and so on and so forth. So you see that it's not that it's just physically not possible if you respect renormalization group flow and quantum effects and all. There is no way you can write an effective field theory with a deSitter minimum in string theory.
The guest of today's podcast is Dr. Keshav Dasgupta. He is a theoretical physicist at McGill University working on string compactifications, especially on achieving deSitter spacetime from string theory, including the possibility of achieving deSitter as an excited state. So let's talk to Dr. Dasgupta and listen to what he has to say. So Dr. Dasgupta, welcome to the podcast. Nice to have you.
Thank you very much. Thank you for inviting me for this podcast. Yes.
So before we talk about anything else, can you tell us a bit about the projects that you are working on nowadays?
Right. So the question that we wanted to answer was that in string theory, can we have accelerating solution possible in string theory, which are interesting because they would be an example of non-supersymmetric solutions and time dependent. So we have to deal with two things, that the solutions are time dependent as well as non-supersymmetric. Along with the fact that since we are looking for something which is accelerated, we also want that the system has positive energy, some kind of positive dark energy or something which is driving this thing. So it turned out to be easier to ask than answer the question because after so previously I've been working on this thing, on this idea for some time, and I strongly believe that solutions would be possible with simple ingredients like branes, fluxes, and quantum corrections that would be able to generate such solutions. Uh, in 2014, I started investigating more seriously, and we found out that, to our surprise, we found out that neither the fluxes, nor the branes, nor perturbative quantum correction, nor orientifold plane, nor anti-branes, none of these can ever lead to uh, a solution, accelerating solution in string theory. So that was a rude shock, I would say, to me at least. And I almost gave up the idea that there could be any such solution possible. So from 2014 onwards, I basically stopped working on this thing because I realized that maybe such solutions are not possible at all. And then came the idea of swampland around 2019 by Bafa and company. And then I got back our usual suspects, all the co-authors of those paper in 2014. And so we again asked that, can we connect this to the swampland criteria? And we found out that there is some connection can be made to these kind of idea that they were saying. And remember, the swampland criteria was, before swampland criteria, there was another paper which specifically asked the question whether string theory has a deSitter minima, and the answer was no, the string theory does not have deSitter minima. So it kind of,
Are you talking about Danielson and Thomas Van Reet, that paper?
that's right, that's right. So, and then, so we said, okay, so that kind of fits with our result in 2014. So we wrote up something saying that it seems like fitting with the idea that we never got any accelerating solution with all the ingredients in, all the available ingredients in string theory. So that was the start of this idea.
So when you say that, whatever ingredients you use, you can't have deSitter, eternal deSitter solutions in string theory. Does that have assumptions like the string couplings should be small and the curvatures should be small, or is it also the case when the curvatures are large, for example? So what I'm saying is that if you go to a random point in the moduli space, would it still be true that you can't have eternal deSitter solutions?
Good. So that was the question. After that, I became more seriously involved in this. And we asked this following question, that can there be a random corner in string theory, like coupling constant is small and all. So again, a new surprise came. We found out that actually the solution that we are looking at has to be time dependent solution. So we looked at it from M theory point of view, just because we wanted to find a solution in type 2B string theory. But type 2B string theory, as you know very well, that it has a lot of moving baggages, a lot of fluxes and all these things. But a dual version, which is M theory, is much more constrained, much more simple, because it combines all the fluxes into one three-form fluxes and all the metric components in one metric. So you have only fluxes and metric and some branes. So we wanted to study this from the dual picture. And we found that the previous 2014 result can be overcome if we actually allow time-dependent solutions. In other words, the internal space and the space-time also should evolve with respect to time. So that was the conclusion there. Then, once we involved time-dependent solution, we found out that the string coupling, which is the dual type 2A string coupling, becomes time-dependent. Okay, so it becomes time-dependent, and we are specifically concentrated on finding something like deSitter solution in flat slicing. So the G string become time-dependent, and so we wanted to see a regime where G string is smaller than 1. So if you impose a time-dependent factor smaller than 1, it actually put a constraint on your time interval itself. For example, if G string is proportional to, G string is proportional to, say, square root of root lambda t, for example. Then if you say that this quantity is smaller than 1, then you can say that t is smaller than 1 over square root of lambda, something like
What
that.
is lambda t?
Lambda is the cosmological constant.
Oh, okay.
Okay. So if we impose that G string is smaller than 1, then we found that the time interval for which the solutions remains under control, it becomes minus 1 over square root of lambda, between minus 1 over square root of lambda and 0. So it should lie between that time interval. Now that was a bit strange. It seems, so two questions arose at that time. That why should we worry about making G string smaller than 1 when we are in M theory? In M theory, G string, can become very large. Why should we even worry about keeping G string smaller than 1? Then came an interesting argument. The argument is that, as I told you before, in string theory, to get an accelerated solution, everything else is red herring. The perturbative corrections, the fluxes, the brane, the anti-brane, the orientifold plane, none of them can help. What can help are the non-perturbative corrections. And the non-perturbative correction goes as e to the power of minus 1 over G string, because these are instant on-like correction. And now you see, if G string is smaller than 1, then that series of e to the power of minus 1 over G string can be controlled. So that was the reason, although we are in M theory, you still need G string to be smaller than 1.
I see.
That put a condition on the time interval itself, that these solutions are only valid between minus 1 over square root of lambda and 0. Because remember, we are doing flat slicing where the time goes from minus infinity to 0. So past is minus infinity and future is 0. And we found that the solutions are late time, and they are only valid in the interval minus 1 over root lambda and 0. So this was a bit of a surprising result. So I was a little bit surprised that we are predicting some limit of time interval. But then something interesting happened from the colleagues of mine. He came and told me that actually this is perfectly consistent with the so-called Transplanckian bound that people have been finding for many, many years. In fact, Brandenburger and company have been advocating this idea that inflationary physics is problematic because it goes beyond this time interval that I was predicting over here, that there will be a problem if we because 1 over square root of lambda is like 1 Hubble radius of that system. If it goes beyond that, there will be problem, and inflationary physics goes way, way beyond that time interval. So there is inherent problem with inflation and all these things. So Robert has been saying all of these things for many, many years. And then Robert told me that your interval of time that you get is perfectly consistent with our Transplanckian constraint that we impose on accelerating solutions. So we got two things in one shot. We got, as they say, killing two birds with one stone. We got a idea that we could have an accelerating solutions. And we found that these accelerating solutions are in fact lies within the valid regime of so-called Transplanckian constraint.
Mm-hmm. So for the audience, can you explain in 1 or 2 sentences what is Transplanckian constraint?
Good. So let me first tell you historically what people meant by Transplanckian thing, what Brandenburger and all. So Brandenburger and all, when they were doing this inflationary physics, they were doing Einstein gravity. And we know that the short distance behavior of Einstein gravity is problematic. Okay, the short distance behavior is problematic. So question is, why should we worry about all of these things? The answer was that in accelerating solutions, something very bizarre happens. And the bizarre thing that happens is that the frequencies changes with respect to time. They get redshifted. Means if you take a very high frequency mode in your theory, then with time that high frequency mode become low frequency because of the expansion of the universe. Now, if you think about it, why should there be a problem? The reason is, if you take Einstein gravity, then the short distance behavior is sick there because Einstein theory is not valid beyond some scale, which means that these short distance modes carry all the sickness of this theory. So since the short distance mode become long distance in the sense that the frequency changes with respect to time, at certain time you will see this sickness, which is at short distance, at large distances also, because with respect to time, which means that the short distance singularity will start coming in our space-time, will enter our Hubble horizon. So then they said that if you put a constraint on the time, which is minus 1 over root lambda and 0, then the short distance mode will not have enough time to enter our Hubble horizon and destroy the physics of that. So that was the reason why they said that there is an inherent problem with inflationary physics. Now, you may ask, why should this idea be a problem for us? Because we know that in string theory, the short distance behaviors are, and by the way, this is called the Transplanckian because these are Planckian regime. So question is, why should this be a problem for us? Because in string theory, we know that the short distance behavior is not problematic. That's what string theory is all about. So why should this idea be a problem? It turns out that this idea is not a problem. Short distance mode don't create a problem for us. What does happen is that if t goes beyond minus 1 over lambda, then G string becomes bigger than 1, as I told you before. If G string becomes bigger than 1, then the series of e to the power of minus 1 over G string becomes not under control. And this series become not normal, and the series cannot be summed up properly, and you cannot get a well-defined effective field theory. So although our reasoning of getting this Transplanckian time is very different from the Brandenburger way of getting the Transplanckian time. We got the same answer in both ways. We got similar answer. And surprisingly, also around the same time, Gyadiwali and company also got a similar amount of time interval by analyzing certain coherent state of these gravitational solution. So there were three different ways by which we reach that same time domain in which the system is makes sense. So that's the idea behind.
I see. Okay, so I think I want to step back a little and try to talk about the quest to get deSitter in string theory from a more systematic point of view, so that the audience can understand what this problem is all about. So, can you explain to the audience that why is it hard to get deSitter in string theory? And first of all, I mean, yeah, I think let's start from here.
Okay, so let's start with very simple ingredient that I need positive energy to create a deSitter vacuum. It's non-supersymmetric and positive energy. The flux can carry positive energy. So why can't I put a lot of fluxes on the right-hand side of my Einstein's equation and get a deSitter vacuum solution? So that's one question we can ask. So for many years, people actually thought that, yes, of course, you can add more flux, you can create more energy momentum tensor, and so you can balance the Einstein's equation. On the left-hand side is R mu nu minus half G mu nu R. On the right-hand side is T mu nu. And you can balance the Einstein's equation. So why does this fail? This fails because of a very strange and interesting reason of gravity. The reason is that once you have a positive source of energy, in usual quantum field theory, it's a nice source of positive source of energy. In a gravitational theory, if you have a positive source of energy, then it creates a negative gravitational potential because it back reacts on the background. So the more you add positive energy, more negative back reaction is created. And the total balance never crosses the positive line. So it's always negative. That's why ADS spaces are so easy to get. So you see, no matter how much energy you add to the system, you'll never get an energy above negative value. So fluxes is ruled out completely. Similarly, brane and an anti-brane also is a source of positive energy, and they back react in the same way to never give you positive energy. Now, when the KKLT paper came up, they thought this anti-brane would help, but we found out that anti-brane also does not help. Maldacena-Nunes condition actually rules out anti-brane. So people even thought orientifold plane would be helpful, can give rise to positive energy. In 2014, we also ruled it out. We found out that orientifold plane suffers actually the same problem as branes and an anti-brane. So we rule out fluxes, orientifold plane, everything else. Now comes the quantum correction, the perturbative quantum correction. That was one of our results of 2014. So we said, okay, now that everything fails, what about a series of perturbative quantum correction to any higher order?
And when you say, sorry, cutting you off. So when you say quantum corrections, you mean curvature corrections or loop corrections?
Curvature correction, G-string correction,
Okay.
everything. You can add M-Planck correction or G-string correction, whatever you add, and in a perturbative series, for example. Why does that not work? It turns out that when we analyzed it, we found that if you write all the perturbative correction in an equation and you stare at this equation for some time, you have a series of Einstein's equations and all this thing with higher order perturbative correction. If you stare at this equation, you'll find that you can add and subtract some of these equations. And once you add and subtract this sum of this equation, the net result was a bit surprising. It shows that to get a positive cosmological constant solution, the net perturbative correction should sum up to a negative definite integer. Okay. Now, this was a bizarre thing because we couldn't figure it out to what order we should have a perturbative correction so that you get a net negative answer. It wasn't clear that whether perturbative correction could add up to give you a net negative answer. And even if it gives you a negative answer up to some order, say, up to some order in M-Planck, up to some order in G-string, how do we know that to the next order in this thing could spoil the thing? So we realized that these perturbative corrections are actually somewhat red herring in the problem. So you see, nothing can give rise to a deSitter solutions in string theory. No perturbative correction, no brane, anti-brane, no plane, nothing can give rise to a positive cosmological constant solution.
So what about non-perturbative corrections?
Good. So question is, can non-perturbative correction give us deSitter solution? Maybe non-perturbative correction can give us a deSitter solution. So we said, okay, let's hope that that works out. Even KKLT was constructed using non-perturbative correction. What goes wrong with this idea? Then came the clash with the renormalization group flow. So let me explain these aspects of the theory. So imagine you are not in a static patch, deSitter. Okay, you want to get a solution of deSitter, which is not in a static patch. If you are not in a I'll come back to the static patch issue a little bit later, because generally people do it in static patch. So we went away from static patch. Let's say flat slicing. So you want to get a deSitter solution in a flat slicing. But there is something very problematic with time-dependent solutions in quantum field theory or in quantum gravity. In a time-dependent solutions, the frequencies are not well defined. The frequencies are actually, as I told you before, frequencies actually change with respect to time. So if you take a short distance high frequency mode, it will very soon it will become low frequency. Now this is a very big problem because remember, renormalization group flow or effective field theory by integrating out high energy mode relies on the fact that you can take a high energy mode, you integrate it out, and you get a effective field theory at low energy. So most of quantum field theory is based on the idea that you can define an effective field theory at low energy when you integrate out these high energy modes. This fails in an accelerating background. In an accelerating background, if you try to take a high energy mode, if you try to integrate it out, by the time you start integrating, it's already become low energy mode. So the whole meaning of Wilsonian integration completely fails. In fact, there is no Wilsonian integration procedure. In other words, in an accelerating background, there is no simple way you can write an effective field theory at low energy. There is no simple way. So what is the way people have been studying so far before we did this coherent state business? People said that maybe, so people agree that this is a big problem. People who actually work on quantum gravity or accelerating, they know that this is a very big problem. So they said that maybe is given by an open quantum field theory. And open quantum field theory is a quantum field theory in which energy conservation is not valid. So, and also in an accelerating background, as the frequency changes with respect to time, energy conservation is not valid also. So for such a scenario, people divide these degrees of freedom into relevant and a environment, and you write an effective field theory with the relevant degrees of freedom such that it continuously loses energy to the environment. So there is a way to do it. There is no action by which you can do it. You do some kind of Markovian process by which you study these kind of phenomena. But this is not very well developed for string theory, and nobody knows how to implement all of these things in string theory, of course. So all in all, you see that no matter what you do, there is no way you can actually have a well-defined accelerating solution in string theory. Perturbative corrections fail, everything else fail. Non-perturbative correction would only make sense if you have a well-defined effective field theory. But such a well-defined effective field theory is not possible in an accelerating solution because this whole Wilsonian method or integrating out method does not work. So you see, there's a very deep problem in string theory that it cannot harbor an accelerating solution in a very simple way.
I see.
So we gave up this idea that it is possible. And around the same time, papers came which says that can string theory have a deSitter minima? The answer was no, and so on and so forth. So you see that it's not that it's just physically not possible if you respect renormalization group flow and quantum effects and all. There is no way you can write an effective field theory with a deSitter minimum in string theory.
Do you think that we have overcome the Dine-Seiberg problem in this context or not?
I'll come back to the Dine-Seiberg
Okay.
problem. But you may say, okay, how about in the static patch? In a static patch, uh, you should not see an issue
Mm-hmm.
because everything is static. You can actually integrate it out. Now, this is where it fails very badly because, first of all, you should notice that unlike black hole or a deSitter case, a static patch is observer dependent. For me, a static patch will not be a static patch for you, which means that if I'm taking a static patch, which is some patch over here, and none of the modes are changing with time, so I can integrate it out and write an effective field theory. For a person, other person who is not in my static patch, he will see that I'm doing a mistake because I'm integrating out those modes which are actually changing with time. I don't see them, but he will see them. So it doesn't make sense. So you see in a static patch, the modes don't seem to change, but outside the static patch, the modes are changing with respect to time. So if you take a Fourier transform, the mode you have integrated out has secretly changing with respect to time. You don't see it in static patch, and you'll be doing a big mistake by writing an effective field. So all of these led us to the conclusion that string theory cannot have a deSitter, at least as a minimum, or as a background solution. It cannot have a deSitter minimum solution.
Right.
Whether
So
or not, yeah.
when you say a deSitter minimum solution, you mean uh, eternal deSitter as a vacuum state. That's what you mean, right?
Yeah, as a potential with a minimum of a deSitter.
I see. Okay,
Okay.
so you do work on something on an idea called deSitter as a Glauber Sudharshan state, right? So what is a Glauber Sudharshan state, first of all?
Good. So then so we gave up the idea of that deSitter could be. In other words, string theory cannot. So our conclusion was that string theory can have complicated potential, but the minima of all this potential could either be Minkowski or anti-deSitter, but not a deSitter minima. Okay, so if you have this like that, so there's a potential of this code. So there cannot be a potential which is like that over here. There's a deSitter minimum, which will all lead to a problem over here. So our conclusion was that string theory can only have a potential with a Minkowski minimum or anti-deSitter minimum, but nothing beyond that. Okay. So that was our first conclusion. So question is, but we see, if you go out, we see that the universe is accelerating. So something is going on. So where is it? So then we found out that, okay, maybe it's something else is going on. That could it be possible that we are, of course, at a Minkowski minimum. Out of all these infinite possible Minkowski minimum, choose one. We are living there, for example. You have a Minkowski minimum, and you have a quantized fluctuation around that Minkowski minimum. So if I create a coherent state of these quantized fluctuation, and in quantum mechanics, a coherent state is very close to a uh, classical system. So if you create a coherent state of all this fluctuation, you can mimic a positive energy solution using this coherent state. Okay, so you can mimic a positive energy solution with this coherent state. So we said, okay, let's create such a coherent state over here. So we created a coherent state. But then we immediately faced a problem. The problem was that in quantum mechanics, the coherent state are created out of free vacuum. And you take a free vacuum, you add a displacement operator, and it's like a harmonic oscillator state you create. Um, you take a free vacuum and you create such a state, and if you leave that state, it will oscillate up and down like a real physical harmonic oscillator. So for every mode, we created such a state over here. But then we face the problem because if you cannot borrow the result from quantum mechanics, the reason is that in quantum mechanics, coherent states are constructed out of free vacuum. But in a theory of gravity or in string theory, there are no free vacuum. You see, there are multiple minimums of them. None of them are free vacuum. They will interact with each other by instantons and all this thing. So there is no free vacuum. So we have to create a coherent state using this interacting vacuum in the theory. So this is slightly different from the usual coherent state. So we called it Glauber Sudharshan state, which is almost like a coherent state, but it's constructed using interacting vacuum of your theory. And we call it Glauber Sudharshan because they were the first person to create coherent state in quantum field theory. So we called it a Glauber Sudharshan state in that sense.
Does this idea come from quantum optics?
This idea comes from quantum optics. Yes, exactly. So in quantum optics, they take free vacuum harmonic oscillator. We instead change everything to take a interacting vacuum in the theory.
I see.
Now, yes.
Mm-hmm.
So that's the start of the idea.
So you were saying something?
Yes. So now, if you create a state like that, interacting vacuum, a state like that, we found again that this state, because of the fact that it's an interacting vacuum and all this thing, this state becomes, the stability of this state depends upon all the neighboring vacuum around it, all the instanton correction from neighboring vacuum around it. So question is, to study the stability, you have to take into account that then there is neighboring vacuum, there's all kind of tunneling going on around there. Okay. So that means that you have to study this state, when we study this state, we have to take into account that there would be a series of quantum corrections coming from the tunnelings of all possible tunneling in these infinite number of wells around it. Okay. So that's where the instanton correction enters this picture. Okay. So question is that, okay, now I created a state over here, and let's assume that it's stable because of this instanton correction. Somehow the system is stable. Question is, can we now justify that it has a positive energy? And what does it mean? Does it satisfy some kind of Einstein's equation? Okay, so that's the question. So, and in other words, what is the metric of that state? What is the kind of metric we get out of these things? So how do we actually compute a specific? Because the background is Minkowski, and I'm creating a state in this particular space time. So question is, what is the meaning of a metric? So then we realized that the metric is actually an expectation value of all the states over here. So the metric appears as an expectation value of, for example, if I take G mu nu as an operator in my theory, then the actual metric that we see is the expectation value of this operator in this particular state. So then our conclusion was that that these accelerating solutions, the metric and everything, is actually an emergent quantity in the theory. That it emerges. It's not there in the vacuum, but because of the fact that we created a state in this theory, it emerges. The metric and all this background actually emerges. So our claim is that the gravitational background is not there. What is there is an emergent quantity, which behaves like a accelerating solution.
Mm-hmm.
Two fell right in the place. One is that it behaves like an accelerating solution. I'll have more to say on this thing. But secondly, we also found that these instanton correction, which are now required, should have G string smaller than 1 because these corrections are e to the power of -1 over G string. So to have a finite series of these things, you need G string to be smaller than 1. So then that brought us back to the Transplanckian issue that we were facing before. And now you see that the whole question of renormalization group flow does not matter because the actual background is static, Minkowski. It's only a state is created inside a static, which means that the modes of your theory are the modes of Minkowski, not the accelerating modes of Minkowski. So you can have a well-defined effective field theory because you can easily integrate out modes in a proper way because they are not changing with respect to time.
Right.
So we overcome that problem of an accelerating solution that the modes will have changing with respect to time. That problem does not appear anymore. And secondly, the time limit of the solution lies between these Transplanckian time domain. So that the start of the idea that it could probably that the accelerating background that we see or the space-time that we live maybe is actually a transient state and it's an emergent transient state.
Hmm. So what you're saying is that this state is built upon a supersymmetric Minkowski vacuum, right? So um, does this state break supersymmetry?
Yes.
How does it
So,
break supersymmetry?
right. So good. So, so this state has to be supported by fluxes around it because, and it turns out that the fluxes has to be an emergent also. Everything has to be emergent. In other words, fluxes, the definition of fluxes is expectation value of fluxes. Everything is now defined in terms of expectation value. So question is, how does it break supersymmetry? Now in M theory, supersymmetry is defined. The supersymmetry is preserved when the four-form fluxes is self-dual. It turns out one condition of being supersymmetry. If you have a warped background in M theory, then one of the results that Sav Sethi, Rajesh and I, in many, many years ago, we wrote a paper. Uh, we discussed that SUSY preserving condition. It was also done by Becker and Becker also had done that. In fact, they were the first to show that SUSY preservation is a statement that the four-form flux defined on an internal manifold has to be self-dual.
Sorry, what do you mean by circular? Is it closed? That's what you mean?
No, I mean the four-form flux, which has to be self-dual. Uh,
Oh, okay. Self-dual. Okay, I thought you were saying
self-dual, not
circular. Okay, I
uh,
see.
the four-form flux has to be self-dual. That was
Hmm.
the condition for that, the supersymmetry to be preserved. So now in our background, since the four-form flux is, since the background is supersymmetry, we expect the four-form flux to be self-dual. So it should be supersymmetric. Now, let's ask back the question, if you create a Glauber Sudharshan state, whose the metric is defined as an expectation value of the metric, the fluxes will also be defined as an expectation value of fluxes. If G4 equal to star G4, there is no reason why expectation value of G4 can also be equal to star of expectation value. And it turns out that is not the case. So when you take an expectation value of this G4 in this state over here, then it's not, although G4 is equal to star of G4, the expectation value is no longer self-dual, showing that this state can spontaneously break supersymmetry.
I see. So supersymmetry is spontaneously broken. Okay. Okay. So
Supersymmetry is spontaneously broken.
right. So one more thing that I was wondering is that so if you look at coherent states in quantum mechanics, right? For example, when you write down coherent states builds up from ladder operators in harmonic oscillator, it turns out that the norm of these states is infinite. Is it the case for Glauber Sudharshan states as well that the norms of these states are in?
Right. So, so the question is that um, so typically the norm of these states are infinite, but you can actually write a normalizing factor in front of it, which is e to the power of minus something to make it finite. Okay, so if you take just alpha expectation value, of course, it becomes infinite. But people tend to put e raised power of minus alpha square in front of it to make it actually finite. No.
Okay, I
So
see.
you can play the same game over here also to make it finite norm states over here. Yes, you can do
Okay.
that.
So suppose that you have this Glauber Sudharshan state, right? Transient deSitter state. Suppose that you want to study fluctuations around this state. These
Yes,
fluctuations, do they also have to be coherent?
good. Excellent question, actually. So, so we asked this question, how do we study fluctuation around that state? Is it another coherent state or something like that? And this brought us to a very interesting paper, which I did not know it existed. It was done by Agarwal and Tara many, many years ago, 1980. They found that if you take a coherent state, then you can create another state using the coherent state, which they call it photon added coherent state. So you add one photon to it. So you have a created coherent state, you can add a photon to it, and you create a new state. And typically they call it Agarwal state. So if you look at the optics, it's Agarwal state. So we said, okay, this looks like something very interesting. So how about we take our coherent state and create something called graviton added coherent state? We'd add one graviton to it, for example, by a graviton operator you add. So we call it Agarwal-Tara state. And if you take an expectation value of the metric in this Agarwal-Tara state, what we found was very interesting. The expectation value of the metric around this Agarwal-Tara state was exactly equal to the expectation of the metric that you find for the Glauber Sudharshan state, plus a fluctuation piece.
This seems like soft theorems. I don't know if it seems like soft theorems, but I don't know if they're
Does look
related.
like a soft theorem. We haven't investigated that direction along. Yes.
Mhm.
So we found out that fluctuation around the Glauber Sudharshan state is another state, which is this Agarwal or graviton added coherent state, the Agarwal-Tara state. So it does go from one state to a different state over here. So one can actually study fluctuations around these things as different state in the theory.
I see. So it means that the fluctuations have to be coherent states as well, right?
Yes, or graviton added coherent state, as they call it. Yeah.
Okay, I see. Okay, so another question that I have is that so in this paper that you recently put out, the 500 pages long paper, there you used duality sequences. So what are these duality sequences and how are they useful, in your work?
Right. So first, let me tell you why that paper became so long. Let's start with that, actually. Why did it become so long?
I mean,
Uh,
the summary of that paper is 80 pages long, which is crazy, I would say.
right. So question is, why did it become so long? The reason is actually, the reason is because uh, as I told you, if you look for a solution, it not only has space time to be time dependent, the internal space also becomes time dependent. Now, saying an internal space becomes time dependent actually creates a lot of issues. The reason is the following. If you take a Calabi-Yau manifold, compact Calabi-Yau manifold, or a non-Kähler manifold, whatever it is, one of the conditions is that to bring back your question about Dine-Seiberg runaway is to put fluxes on it so that it creates a potential so that this guy does not run away to become infinite size, which is the Dine-Seiberg. Two things happens now. If you put fluxes on a compact space, the Dirac quantization has to be satisfied. Otherwise, you cannot put fluxes on a compact space. Otherwise, the system will be unstable. Now, in a time-dependent background, when the system is changing with respect to time and the fluxes are changing with respect to time, how do we know that the system satisfies Dirac quantization? Or what does the Dirac quantization mean in this setup? Okay, that was one question. In M theory, there is yet another problem. If you put fluxes on the internal manifold, you better make sure that the anomaly condition is satisfied. In other words, the integral of the fluxes should be equal to the Euler characteristic of the internal manifold. This was for Calabi-Yau manifold. Otherwise, again, the system will become unstable. So in our case, when the system is changing with respect to time and the fluxes are changing with respect to time, how do we know that the anomalies are not cancelled? Anomalies are not there. Maybe the anomalies are there, they're making the system, which means you have to look back all the equation of motion for fluxes. So you have to not only look at all the equation of motion for fluxes, you have to look at all the Bianchi identities for all the fluxes component. And you have to look at the flux quantization for all the flux component. You have to look at anomaly cancellation for all the flux component. So you have to look at all the equation of motion all the Bianchi identities, all the anomaly cancellation for every flux, and all the flux quantization, and give a meaning to what all these mean.
Right. I
That
mean,
created,
sorry, go
yeah,
on, please.
that created a hell of a problem for us. It took us years to figure these things out. Otherwise, you cannot claim that we can have a solution of any kind, because unless you satisfy at least the minimum set of requirement. So this took us years to put in together. Each and every flux component need to be checked. And you know that these solutions are not valid perturbatively. So you have to go to the non-perturbative regime and see whether these make sense or not.
Mm-hmm.
So that opened up floodgates of problems after problems after problems. So we had to make sure they all make sense. And eventually, after a lot of work, we eventually found out a setup that it does make sense. So that was a sizable part of the paper, just to check the consistency of all these equations and all.
Yeah, so I was going to say that this is the reason why a lot of subheadings are very similar, but they're for different flux components,
That's
right?
right. That's right. That's
Yeah.
right. So yeah.
So my question was about duality sequences. So why are
Yes.
they important?
Right. Good. So the previous work was to find the deSitter solution in the type 2B theory. And remember, I told you we took M theory, so you have to go from M theory to type 2B theory. The way to go from M theory to type 2B theory is that if you take the M theory torus and you shrink the torus to zero size simultaneously, then one might think that you go to 9-dimensional theory. Actually, you don't. You go to type 2B theory, fully non-compact type 2B theory. Okay, so you have to. This was known for static solutions. Okay, so um, now comes the problem, because now everything is time dependent. So if you took the M theory solution, I told you this time dependent solution over there. So, and you look at the 11-dimensional torus, you'll find that the 11-dimensional torus develop a time dependence in which it's shrinking, automatically shrinking because of the time. So you don't have to compactify, it automatically will shrink. So question is that if you leave it just like that, 11-dimensional torus will shrink, and at some point it will shrink to zero size. That means you don't have to do anything. Take a 11-dimensional theory, wait for a little bit time, it will go to directly to type 2B theory, because the 11-dimensional torus will shrink to zero size. And as soon as it shrinks to zero size, it becomes a non-compact n-dimensional theory. So from M theory to 2B, we didn't have to do compactify. It automatically is doing to you. The theory automatically is flowing to type 2B theory, because of the fact that everything is dynamical. So you don't have to come. See, in a static background, duality or T duality is that you take a radius R, you go to 1 over R, the radius and all, right? T duality, or all the duality, you have to shrink some cycle to zero size and all. But
Right.
these are for static background. For a time dependent background, cycles are themselves changing with time, because the internal manifold is changing with time. So we cannot just go in and shrink some size to zero size. Since it's changing with respect to time, we have to see how it automatically goes from one to another.
So wait, I have a question here. So you said that start from an 11-dimensional theory on a 2-dimensional torus. When you say that the size of the torus will shrink to zero, you mean one of the cycles will be much
No, both.
smaller than the other cycles?
Both actually simultaneously will become zero size. Then only you can
Oh,
go back to B theory.
but then you get type 2B theory compactified on a circle.
It does not. So that's the
Okay.
surprise. That was shown
Hmm.
by John Schwartz many years ago. You might think that actually what actually happens is that take M theory on some manifold with a toroidal direction.
Hmm.
So let's go it sequentially. If you take, so torus has two directions. Say, let's call it one direction is 11, other is 3. Let's call it okay. So let's go sequentially. If you shrink the 11 direction, you should get to type 2A.
Yeah.
And if you start shrinking the third direction, at some point, as you start shrinking the third direction, you're still in type 2A. But as soon as as soon as the cycle becomes smaller than alpha prime, it dedualizes.
Yeah.
Okay. So now you see that if you shrink both the cycles simultaneously to zero size, the 11th cycle, when it shrinks, it goes to type 2a. The
Yes.
3rd cycle, when it starts shrinking, at some point it becomes type 2b of a radius 1 over r. And then when it shrinks completely to zero size, it
Oh,
becomes a
now I
non-compact.
understand. Yes. Okay. Makes sense. That makes sense.
So that's what happens if you take. So now that you don't have to do anything because it's time dependent, it'll automatically do the job for us.
Mm-hmm.
And it was very easy to see for us that it's actually automatically is taking you to type 2b theory. Okay, so that was previously. So then we asked
Mm-hmm.
the question, can we go to the heterotic side by playing similar kind of game over here? So of course we'll go to type 2b. Easily we can go to type 2b side because of this thing. How do we go to heterotic side? So, so we started thinking about it. So we said, okay, let's assume that this M theory manifold is a 6-dimensional manifold times a torus. Okay. So when it shrinks, when the torus shrinks to zero size, you get type 2b on this 6-dimensional internal space. Okay, so far so good. And it stops. The sequence stops and you get a nice uh, deSitter kind of solution as a Glauber Sudharshan state in 2b theory. Now, we said, how about let's take this 6-dimensional manifold in type 2b as a 4-dimensional manifold times an orbifold actually times an orientifold. And let's assume that the 6-dimensional manifold also has some time dependence. Okay. So after this 11-dimensional torus shrinks, and we claim that these 6-dimensional manifold, that other torus of the 6-dimensional manifold shrinks very slowly. Okay. So by the time the torus shrinks to zero size, you go to type 2b theory. But in type 2b theory, things don't end because that internal 6-dimensional torus also starts shrinking. And as it starts shrinking, something very surprising happens if you have an orientifold. When you start shrinking the torus, an orientifold action actually takes you to type 1 theory. This was shown by Ashok Sen, that if you take a type 2b on a M4 time a toroid orbifold, and the orbifold has an orientifold point, and you start shrinking this toroidal orbifold, then you actually get type 1 theory. Type 2b should go back to type 2b under T duality and so on, because there
Mm-hmm.
are even number of cycles shrinking to zero size, you should get type 2b back to type 2b. It does not happen. It turns out that actually type 2b theory actually becomes type 1 theory.
So, as far as I understand, if you want to get type 1 from type 2b, you have to do, the orbifold under worldsheet parity. So, do you get something like that under this
Yes,
shrinking?
exactly that happens because that orientifold action has an orbifold and a worldsheet parity
Hmm.
because of the fact that it's an orientifold background. And so when you shrink this to zero size, a T duality of omega and -1 F left and Z2 becomes omega only, which means that it becomes type 2b modded out by omega, which is type 1 theory on a torus. Okay.
I see.
You have a change in topology also, and you get a type 1 theory on a torus. Okay.
Mm-hmm. Okay.
So we got a type 1 theory. So you see, it's automatically doing it. You don't have to do anything because of the fact that there is a time dependent, it's automatically shrinking. And so it's taking us to type 2b and it's automatically taking us to type 1. But we are not done yet
Mm-hmm.
because now we look at the coupling of type 1. We find that now I told you the couplings are also changing with time. So we look at the coupling and we find to our surprise, the coupling is actually increasing.
Yeah.
As the coupling increases, the theory goes S duality.
Mm-hmm. And you go to heterotic theory.
Go to the heterotic and it stops. After that it becomes weakly coupled and things stop. So you see the system dynamically goes to heterotic side. So that is our dynamical duality sequence.
I see. So, when you say it goes to heterotic, you mean SO32 heterotic, right?
Yes, so 30, absolutely. So question is, how do we get the E8 cross E8 heterotic?
Well, you T duality.
Of course, T-duality, but we don't want to do T-duality. It has to automatically do our job.
Yeah.
T-duality would have done it, of course. We want to automatically go. So for that, we found out that you need to make a much bigger picture in which you have to put three warp factors, changing with time in some specific ways and all. And then you can dynamically also go to the E8 cross E8. Horava-Witten kind of picture, yeah.
I see. That's interesting. Okay. So can you make such? I mean, so as far as I understand, this Glauber Sudharshan state, it's built on supersymmetric Minkowski vacua, right? Um, can you start from the well-known three non-supersymmetric string theories, for example, the Sugimoto model or the
Yeah.
O16 model, and get a Glauber Sudharshan state? So, is it possible, or have you looked into it yet?
Question is, why didn't we directly start with non-supersymmetric theory? The reason is that supersymmetric theory gives us one thing that the zero modes cancels out. Okay, so the 0 point energy cancels out completely from boson and the fermion.
Mm-hmm.
Why do you want to do that? The reason is that the 0 point energy can be renormalized to be of the form m Planck to the power of 4. But we know that the cosmological constant is 10 to the power of minus 122, 20 times smaller than that quantity. So clearly the cosmological constant, whatever it is, cannot come out from the zero mode thing. So we wanted these headaches to go away. So we took the supersymmetric background. And then I will answer your question, where does the cosmological constant comes in our setup? So at least the zero mode has no contribution to the cosmological constant in our construction. So that is one of the reasons why we did not want to start with any non-supersymmetric background from the get-go. We wanted to have no contribution of the 0 point energy at all in that system. So all the positive energy should come out from the spontaneously broken supersymmetry. So question is, where is this energy coming from? And there came another issue, which it's a big problem in quantum field theory, which generally people ignore it. The issue that appears is the following, that, as you know probably very well, that perturbation theory does not make sense because perturbation theory is asymptotic, because the Feynman diagram grows factorially, which means that at some point, perturbation theory will not make sense. Even if you take G string to be, even if you take the coupling to be smaller than, much smaller than 1, at some point it will just blow up and the answer will become perturbation theory will not make sense. But we ignore it. It was first pointed out by, of course, Dyson, that in QED also the same thing happens. But we don't have to worry too much about it because we don't go beyond. And we know, and a small calculation will tell you that QED starts becoming bad at around 300th loop. So we never go to that order of this thing. Okay. So you can still rely on perturbation theory. So, and not worry about what's going to happen. And the way out is that, of course, perturbation theory in quantum field theory, Feynman diagram grows as n factorial. So you have to Borel resum everything. You have to take first you do a perturbative calculation. And if you include all higher order, then you have to Borel resum the whole thing to get any finite answer out of that thing. But we rarely do such thing because we never go beyond 5, 6 order in perturbation theory. So, but in our case, when we calculate the expectation value of the metric in this Glauber Sudharshan state, we found that this expectation value of the metric can be written as a path integral in this theory. So it's a path integral of this metric component. So then we asked to what order we should do this path integral calculation. Okay, so you have e to the power minus s, d of whatever degrees of freedom times metric, but s is shifted by this Glauber Sudharshan state. That's why the 1-point functions are non-zero. Of course, that's the reason why path integral makes sense of 1-point function. So question is e to the power minus s. I can write it as s kinetic plus s interactions. So e to the power minus s interaction, to what order should I expand? And it turns out that you have to expand to all possible order. You have to sum up all possible things, which means that you have to look into the fact that it actually, perturbation theory is screwing up at some order n. Okay. And we know that in string theory, perturbation theory grows as n factorial square. Compared to quantum field theory, it grows as factorial square, as was also proved recently by Mirza Khani and others, who actually showed that this is how it grows. So if you take everything into account, it turned out that an expectation value of the metric that we computed only makes sense if you Borel resum the whole thing properly. Okay. So if you Borel resum the whole thing, then something very interesting happens. Then we found out that once you Borel resum, then you get an emergent energy, positive energy to that system. Okay. Telling us that maybe the cosmological constant is actually an emergent quantity, which we'll never see at any order in perturbation theory. Maybe this is one quantity you can only see after you sum up everything, then suddenly you'll find that the system has a positive energy. So in our case, we found that indication, first indication that it's very important to sum over all order. We took a very toy model, of course, we could not do the real thing. In a toy model, we found, to our great surprise and all, was that only after you sum up this whole series using Borel resummation, the system shows that gives an indication that there is a positive energy to that system, which we interpreted as a cosmological constant. So the cosmological constant, which we believe is something that we will never see at any order in perturbation theory. It's an emergent quantity, is only visible after you sum up all of these things properly. Okay, so that's how we got the positive energy for our system. It did not come from the 0-point energy. Now, you might ask the question, how do we know that this is 10 to the power of minus 120 times smaller than m Planck square, for example? We don't know the answer to that question, whether how small can it become, because we haven't summed up everything. We just took a toy model. So a toy model gave us an indication that the system has a positive energy. But that positive energy, you cannot see it any order in perturbation theory unless you sum up all of these properly.
So you were, by the way, I have a question here. So you are still talking in the context of Glauber Sudharshan states, right?
Yes,
Right.
that's
So
correct.
would it be correct to, so I don't know what you're calculating there, but would it be correct to call it the cosmological constant, or is it something else that you're calculating there?
Exactly. So it's some positive energy. How do we know it's a cosmological constant? Okay.
Is it even a constant?
Yeah. So is it even a constant? That's a good
Yeah.
question. So in our previous paper, we found that at least there's a constant piece. At least there is a constant piece over here. A more careful idea showed that this is actually not a constant, but it has a small, slow time variation, very slow time variation, which was in the beginning was a bit disappointing for us. But then the DAISY result came up. And that's why we wrote that paper. And another interesting thing happened, that if you try to manipulate your theory and try to make it as a constant and ignore all of these things, the calculation becomes more difficult to do. But if you honestly and take the fact that there is a small time dependence, somehow surprisingly, some of the calculation simplifies in this setup. So what we are getting is that we are getting some kind of hint that there is a positive energy, but that positive energy has a small time dependence. It's not a constant actually.
Okay.
And it's,
Yeah,
and
please go on.
it's decreasing with respect to time. And it
Oh,
comes
it's
exactly as
decreasing.
a
Okay.
piece which is on the right-hand side of the Einstein's equation. It does seems like it is a cosmology. So it comes as R mu nu minus half G mu nu R. Instead of lambda G mu nu, you have some time-dependent factor which appears from all these quantum corrections.
Um, but okay. So I have some questions regarding to that. So I mean, it may be a naive question, but it's still a question that's coming in my mind. If you have a time dependence for, a cosmological constant, doesn't that violate Lorentz invariance?
Doesn't that?
Violate Lorentz invariance.
Well, we are already chosen a background.
Oh, okay. I see.
Yeah, we have chosen a background. Yeah, very good question, actually. Can we have a background independent picture of all of these things?
Hmm.
Can there be a nice Wheeler-DeWitt equation for this thing? Hamiltonian vanishes and all this thing.
Yeah.
That's a much harder question you are asking that we don't know yet.
Okay.
Also choose a background. So see, you rose a very interesting question because uh, once you choose a background,
Yeah.
which we choose Minkowski and whatever state, and once you choose a background, you have a well-defined notion of a time. So there is a meaning of time in this thing because there is a proper slicing, ADM slicing you can do, ADM energy you can do, and no worries about the Hamiltonian vanishing. In other words, once you choose a background, you have a well-defined notion of a time. So e raised power minus I h t evolution makes sense. The Hamiltonian does not vanish. The Wheeler-DeWitt equation does not screw up your process and
I
all that.
see.
And Lorentz
Um,
invariance, you already don't have to worry too much about that.
mhm. So, okay, I have one more question. It may be related to the first question that I asked, but let me ask it anyway. So, the usual reasoning for why we can include this cosmological constant term in the Einstein fields equations goes as follows: that you have this combination r mu nu minus 1/2 r g mu nu, and we do know that the covariant derivative of this particular term is zero, which is the same as the covariant derivative of the stress tensor. And we do know that the covariant derivative of the metric tensor is zero, which means that any term proportional to the metric tensor can be included on the left-hand side. But if you have time dependence for lambda, it's not a proportional term to the metric. So the covariant derivative of the left-hand side, does it still vanish?
Yeah, good. So it turns out that we never get a lambda g mu nu kind of piece. Okay.
Okay,
What we get is the T mu nu piece over here. So it's R mu nu minus half G mu nu are equal to T mu nu. Okay. The
okay,
T mu nu energy momentum tensor that you get is instant on sum. All the, as I told you, the perturbative and all red herring in the problem are this instant on sum over here.
I see.
This instant on sum is what is get screwed up in the sense that because of the fact that perturbation theory is not well defined. So what you get on the right hand side is one instant on contribution plus two instant on, three instant on, so on. In other words, you get a trans series on the right hand side of your equation,
Yeah.
but you get a lambda g mu piece over here.
Okay, so it's not the usual cosmological
No,
constant
it's
term
not
that
the
one
usual
gets.
it
Okay,
appears. No,
that
not
makes
the usual.
sense.
Otherwise, all these issues would come in.
Hmm.
Um, it never appears in the usual way like that. Yes.
Okay, that makes sense. Okay, so another question that I have is that this Glauber Sudharshan state, how does it evade all the no-go theorems of deSitter?
Very good. So let's first ask the question that the no-go theorems, let's ask the question, the no-go theorem was the fact that Maldacen and Nunez was that fluxes and D-branes and anti-D-brane cannot give rise to a deSitter solution. But as you know, we never take perturbative, no D-brane, nothing, all this thing. Okay. Secondly, the no-go theorem also says that O-planes and all will never give rise to a deSitter. We also remove O-planes from our picture. The only way you can get a deSitter is when you go to the non-perturbative uh, thing, which is exactly what we are taking. So what are these non-perturbative objects we are taking? So these must be the instanton. So what are these instanton in M theory picture? So this non-perturbative is this 5-brane instanton, which wraps the internal manifold, or 2-brane instanton, and so on and so forth. Okay. Now, this 5-brane instanton are this Becker-Strominger instanton, also called the BBS instanton. And these 2-brane instanton are these, if you dualize to type 2b, are these KKLT instantons, which KKLT had taken. What we found in our analysis is that the KKLT instanton are actually subdominant. They do not contribute as much as the BBS instanton, the Becker-Strominger instanton. So the no-go theorem, to answer your question precisely, are evaded precisely by these non-perturbative objects, which are the wrapped fibrines on this internal six manifold, which are the fibrin instanton, the BBS instanton. They give rise to positive energy in the system. Okay, question is, why are they doing the acceleration? Why are they accelerating the background? Because there is no cosmological constant to actually accelerate the background. Where is the acceleration coming from? The acceleration is coming from the fact that this BBS instanton are this instanton in the internal manifold, okay? Okay, which means at every point in the four-dimensional space, there is this wrapped instanton at every point in this four-dimensional space, okay? And as I told you, because of the time dependence, the size of this internal manifold is changing. So these instanton are actually becoming bigger in size, which means that at every point in our four-dimensional space, there would be something which is growing at every point. This is exactly the one which is pushing the space outward to accelerating the space over here. So you see this Maldacena-Nunes kind of no-go theorem is overcome from the fact that we are taking these non-perturbative corrections into account, which are non-perturbative objects, which are beyond the Maldacena-Nunes thing, and the higher order curvature term which come because of the influence of this non-perturbative effect. So this is the precise way we are violating the non-perturbative.
So what about the theorem from Kutasov and collaborators, KSSM theorem?
Yes. So that we had an elaborate section on that thing, how it is. Right? So let me explain to you what KSS, Kutasov, KMMS.
KMMS, sorry, yeah, not
So
KSSM.
Kutasov, Melnikov and all, their claim is that if you take a heterotic theory, and if you demand that you want a deSitter solution in the heterotic theory, then that deSitter solution will have a SO 1,4 symmetry. Which you can, if you do a Euclidean space, it will be SO5 symmetry. And now, if you want to study a worldsheet theory with SO5 global symmetry, then that worldsheet, this SO5 will appear as current in your theory. Okay, and this current will give rise to a CFT with specific number of central charge. And if you demand SO5, then one can show that you cannot accommodate these SO1, SO5 symmetry in the CFT. Okay, you cannot accommodate this because it's too big a size that can be accommodated by the central charge constraint in your theory. Thus, SO5 global symmetry cannot be accommodated in this theory, thus ruling out a deSitter solution completely. Okay, so how does this is overcome? The KMMS theorem uses alpha prime correction, but no G-string corrections. And so that's one issue. There is a series of alpha prime correction, which is they take worldsheet instanton, but no G-string correction in your theory. And secondly, KMMS theorem relies on exact SO 1,4 symmetry of your theory. Now come back to our analysis. Our analysis specifically relies on G-string corrections, which are non-perturbative correction, which are not included. And secondly, since our space is transient, it does not have an exact SO 1,4 symmetry because it's not a deSitter. It's secretly Minkowski because asymptotically it becomes Minkowski. It's only deSitter for a very limited amount of, or at least behaves like a deSitter for a limited amount of time. Asymptotically it becomes Minkowski. So it never has an exact SO 1,4 symmetry inside. So it's non-perturbative and it does not have so it completely takes us away from the KMMS constraint, and hence they are not relevant for our analysis over here.
I see.
There are many other reasons. We tabulated those reasons in the introduction of our paper.
I think I saw that. Yeah, and I think I'll also put that in the podcast in case someone wants to read that. So one more thing that I want to ask you is that people do study different backgrounds of string theory, but they also want to study the worldsheet description. So for Glauber Sudharshan state, do you have a worldsheet description?
Right.
Can you have it?
Yeah, the answer is so far it appears that there is no simple worldsheet description possible in this kind of theory because of the fact that they are transient state in the theory. There is no single worldsheet description that can capture this behavior of this kind of theory. So if there exists a worldsheet, it will be some kind of strange combination of worldsheet that give rise to or some kind of thing. But it appears that such a transient state at least can be studied from bulk point of view, but worldsheet description appears to be not possible at least in a simple way. Because
Is it
no
hard or is it
worldsheet,
not possible?
huh?
Is it hard to get or is it not possible to
I
get?
think there's no single worldsheet description that can capture such transient state. The reason
Okay.
is the following. If you have a worldsheet description, then such transient state should have a vanishing beta function condition for the worldsheet thing.
Mhm.
Okay. But a vanishing beta function condition will always give rise to eternal solution.
Okay.
But these are very small transient state solutions, like they appear and go away.
Hmm.
So there cannot be a simple, at least a single worldsheet description cannot capture. Maybe some kind of thermal average of worldsheets can be there or something, or in string field theory description would possible, but not in a simple perturbative worldsheet description that can capture.
Okay. And if suppose that
Again,
if there is some, sorry, please go on.
again, we have a detailed discussion of this also in our introduction of our paper. There is a section which says that can these states exist as a worldsheet description? The answer we found after a lot of analysis is that no, there is no single worldsheet description possible for such transient state in the theory.
Okay. And um, suppose that if there is a worldsheet description, do you expect this worldsheet description to be supersymmetric? Because the bulk theory doesn't have supersymmetry. But there are
Uh,
many cases where the bulk theory doesn't have supersymmetry, but the worldsheet is supersymmetric. So
yes,
what do you expect?
I don't know yet. I'm not sure that's possible at this stage. It appear so we have a supersymmetric background that, of course, has a worldsheet description. But
Yeah.
once you create a state like that, the bulk theory, as you correctly pointed out, does not have supersymmetry and all. These are also transient states. So at least our conclusion was that there is a single worldsheet cannot capture these kind of things. So maybe in string field theory, there is some description possible. But beyond that, we don't know the answer to that question.
Okay. And let me ask you a similar question. So although the quest for deSitter CFT correspondence is, I mean, it's not as successful as ADS CFT correspondence, but do you think that, one can find a holographic dual for these Glauber Sudharshan states?
Excellent question, actually. Um, Again, these states are transient state. They don't have full SO1, 4 symmetry as far as.
Mm-hmm.
And so far deSitter CFT is to map this SO1, 4 on one side and CFT on the other. At least that is
Yeah.
the. We don't know exactly whether these have any symmetry or normal symmetry of this form. So at this stage, it's not clear whether this Glauber Sudharshan state will have a simple dual CFT description for this thing.
Okay. Let me be more general then. If we don't have a CFT description, do you think that we can have a non-gravitational theory on the boundary? It doesn't need to be
Ah,
a CFT.
probably possible.
Okay.
But that's a very good question, actually.
Okay.
And
One more question that I have, based on what you said, is that the internal space grows as well, right? It's
yes,
time dependent. So, do you think that if you start from some scale separated solution, it can become a solution which is non-scale separated, because that will be a problem?
yeah, that will be a very big problem. It turns out that um, if it become so, it turns out that luckily for us, it's uh, something very also interesting happens. Um, uh, let's take the type 2B example. Okay,
Hmm.
when you dualize to type 2B theory, when we dualize to type 2B theory, the time dependence of the internal space become very, very small, very small. And the size of the internal space is, so scale separation is not no longer a problem. ADS CFT, there is a problem of scale separation, ADS 5 plus S5. We cannot have a scale separation because size of ADS5 and S5 is exactly similar, so there is no scale separation. That's why ADS5 cross S5, you cannot say that I have a 5-dimensional theory and internal space is separate. In this kind of theory, if you take the size of the internal manifold to be small, start small or anything, in the dual side, it does not change very much. So this issue of scale separation is there. So there can be a nice scale separation so that you can actually define a 4-dimensional theory and an internal theory. In the SO32 theory, something even more interesting happens. In the SO32 theory, although in M theory picture, the size of the internal manifold changes with respect to time. Once it comes to the heterotic side, SO32, the internal space become time independent. Okay, and it become very small, so scale separation is still there. In the E8 cross E8 side, somewhat similar thing happens, but the internal space does not exactly become time independent completely. But the time dependence is very weak in the E8 cross E8 side. And the scale separation is valid there too. So you can actually make sense of a 4-dimensional theory and an internal space. So that issue does not plague us.
Okay, so I have like a couple, one more question about this program, and then I have
Yeah.
a couple more questions, on being a physicist, and then I have some questions from the people. So one question that I have about this, well, actually two questions that I have about this program. The first question is that this, program about deSitter being a Glauber Sudharshan state, does it satisfy all the swampland constraints? Have you checked all the swampland constraints, or do you still have to check some?
Yeah. So one of the major swampland constraint is the Transplanckian TCC conjecture. That is automatically satisfied by our construction. So that we already checked. The other swampland constraint are we have verified some of these things and we found out that you can satisfy these swampland constraint. It appears to be satisfied.
For
But
example, the no global symmetries, is that satisfied?
we haven't checked that aspect thing.
Okay.
So, but remember, the swampland is constrained are for the vacuum solutions.
Yeah.
Ours are at the vacuum level, of course. It is a supersymmetric Minkowski, so there is no swampland constraint at all. We are transient excited state, which are not exactly covered by the swampland because swampland
True.
captures deSitter minima solutions for deSitter minima or whatever it is. That those solutions are not there and they are vacuum solutions. But we have gone across that because at the vacuum level, it's supersymmetric Minkowski, so there is no swampland constraint.
Okay.
It's a transient excited state in the theory, so not exactly captured by the swampland. But as Robert and other pointed out to me, finally after so many revision of the swampland constraint, the final conclusion is that as long as the system satisfies the Transplanckian TCC bound, you should be okay.
I see.
These are by
Okay.
construction satisfy the TCC bound. So, but then again, it's not exactly related to the swampland criteria because swampland deals with vacuum solution. Ours is a transient excited state in the theory. Two different
Okay.
altogether.
I see. Okay. So one
Uh,
more thing that yeah, sorry, go on.
Sorry. And secondly, about the global symmetry that you are asking. Um, uh, so remember, the way what we did was that when we wrote down an effective field theory, we integrated out all the high energy mode and we came to a very low energy where there are finite set of degrees of freedom in our theory. Okay. And using these degrees of freedom, we created these excited state in the theory, which means these excited states are given in terms of these degrees of freedom. So there is no extra global symmetry are required for this because we have already integrated out all the unnecessary things in your theory. And these excited states are defined with this limited number of degrees of freedom and higher order correction, all the irrelevant operators associated with those kind of things. So all other degrees of freedom, which creates problem in the swampland thing, are not there in our analysis because we have already taken care of these things. And with this limited set of degrees of freedom, which are the massless degrees of freedom, we constructed these excited state in our theory. So in that sense, swampland criteria would all be satisfied in that sense, if you want to really compare with the swampland.
Okay, I see. Another thing that I wanted to ask is that can you embed standard model in this thing, in the Glauber
Yes,
Sudharshan paradigm?
it's very, very good question. So let's ask a theory that is easily standard model appears, or at least the non-abelian gauge theory appears, is E8 cross E8 heterotic theory. Okay. So what we found was that in our this dynamical duality sequence, we found that we can get this E8 cross E8 theory. And these E8 cross E8 theory are coming from exactly this Horava-Witten theory, in which, remember, in the Horava-Witten theory, you have M theory on S1 mod Z2 with two Horava-Witten walls, and you have these two E8 things. The difference in our case is that we also have two walls over here, but the walls are moving towards each other. And at some point, the motion stops. At some point, the motion stops over here. And you can, at that particular point, you can have this E8 theory broken to whatever theory you have on the 3+1 dimension, because there is a well-defined hierarchy in your theory. And then the system allows a specific realization of gauge theory in 3+1 dimension theory. Now, how is the E8 broken to the standard model that we haven't yet investigated? We did find that this whole system is consistent with axion constraint that's come from axion cosmology and all these things. So that we have checked.
Okay.
Uh,
I mean,
haven't
one
checked.
question. Sorry,
Yeah,
please go on.
we haven't checked the whole whether we can get the full standard model scenario here, but at least we have the um, model to realize these things. So in an accelerating background, yes.
So you said that these walls stop at a non-zero distance. So what makes them stop? Why can't they just collide?
That's a good question. These walls has some charges on them. So when they come very close to each other, there is a repulsion of these charges. And the repulsion and the gravitational attraction balance each other, and the dynamics actually stops there.
I mean, it may be a naive question, but it seems that you can also probably talk about weak gravity conjecture here, if
We
possible.
could, yes. Yes. So there are options over there, that thing, but we are investigating all of these things, and you are welcome to join in.
Sure. I mean, I would love to. I mean, I will need to read your very long papers, but I would love to be honest.
Yes, most of the detail, as I told you, just to verify that it makes sense.
Sure.
The main content of the paper is very, very
I'm talking
simple.
about your past papers. I mean, they are like 100 pages easily, so they're not short either.
Again, just to verify it makes sense that
Sure.
these solutions make sense. That's everything.
So actually, one question that I wanted to ask earlier and I forgot was that when you were talking about including all the terms in the perturbative expansion, I was going to ask a question, but it may be a naive question. So forgive me if it's a naive question. Uh, the question was that for your work, do the supersymmetric localization techniques, are they relevant?
From the okay, good. So from the Minkowski point of view, it would be where it is coming in is remember I told you that the perturbation theory blows up some point. So what would be the correct way of introducing these issue in your theory? There is no simple way to introduce, but people have found at least one way to tackle this thing is to say that you take the whole perturbative series in your whatever way you want to write this perturbative series, and then you know that at higher order this perturbative series will blow up, uh, and then to control this blow up you add the first instanton. You take the instanton correction and you study the fluctuation around that instanton. Where is this your localization trick will come in? You take the fluctuation around the first instanton. The first is the zero instanton sector, and you assume that this perturbative series is the fluctuation around the zero instanton sector. Okay. If you calculate any expectation value over this series, it will create problem because of the factorial growth. Okay, to avoid that, you add the first instanton correction to your theory, add the first instanton and study the fluctuation around your first instanton, which will involve this localization technique to do the calculation because you're doing a saddle point calculation over here. Okay, so you take the instanton saddle and you take the fluctuation around it. Now, if you calculate the expectation value of any observer or observable or an operator, it will again show a factorial growth. To avoid that, you add the second instanton into account and you study the second instanton saddle and you study the fluctuation around it. So you see your action now takes a very interesting form, which is the perturbation around a zero instanton sector plus one instanton saddle, perturbation around it, plus two instanton saddle, the perturbation around it, three instanton, and so on and so forth. So your action takes this trans series, this is called a trans series form. So your action takes this trans series form in your theory. And the supersymmetric localization actually fixes this coefficient of this trans series, at least to a few order. So this is where the supersymmetric localization becomes immensely useful. And remember, our background is supersymmetric. So you can use that kind of action. And now in this action, the perturbative part will, some part of perturbative part will give you R mu nu minus half G mu nu R. And all other thing will go to your right-hand side of your Einstein's equation. And this will give rise to this so-called cosmological constant.
I see.
It
Okay.
comes from all of these corrections over here. So you don't actually get a lambda G mu nu piece, of course, but you get something which a consequence of these trans series.
Okay. So one last question about this line of work is that if you had to list some major problems that one should work on if one is interested in this Glauber Sudharshan paradigm, what would you say?
See, one of the issue that I think we should clarify is there a nice, as you also asked, CFT way of realizing all of these things? Is there a string field theory picture which can actually capture this kind of analysis over here? That's one most important thing. The other important thing is that we are claiming that the energy is coming from, the positive energy is coming from summing over all these, by Borel resumming all these thing. How do we know that this is very small? Remember, the energy has to be as small as 10 to the power of minus 120 times m Planck square. If you take the 0-point energy, it could give you energy up to m Planck square. Nothing smaller than that. How do we know that energy is smaller than 10 to the power of minus 120? Our initial analysis showed that the energy can be made small, quite small, but we don't know how small it can be made. And does it actually give rise to the cosmological constant? Secondly, we found that there is some time variation. Does it really fit with the time variation that DAISY is finding? And secondly, what if the DAISY results are a fluke? They may not be. So what does it mean in our model? If the cosmological constant, it actually does not vary with time. It seems that it's more natural that the cosmological constant, whatever it is not a constant, it's a dynamical dark energy. So these are few issues we are thinking of that. And another issue is, of course, which I found to be more interesting is that can we compute the wave function of the universe? Can we show that the Wheeler-DeWitt equation appears from this setup? Our initial argument with a paper with my student, we found that the Wheeler-DeWitt equation actually appears if you take, instead of taking only one Glauber Sudharshan state, if you take all possible choices of Glauber Sudharshan state, so you can take all possible. So for each and every Glauber Sudharshan state, you can calculate the expectation value of the metric. Most of them will not be a deSitter, it will be something else, of course. So if you take all possible Glauber Sudharshan state in your system, we asked, is there a meaning of the wave function of the universe in this case? And we found out that if you take all the Glauber Sudharshan state, And if you write an envelope wave function, which is connect all the Glauber Sudharshan state, that envelope wave function we found satisfy the Wheeler-DeWitt equation.
Okay.
That
Is
was
that
one.
surprising or not?
That was very surprising to us that it satisfy a Wheeler-DeWitt equation. We could derive an emergent Hamiltonian killing that wave function over here. So this led us to the question. This has led us to a very important question, which I think we are trying to answer now. We should answer now, is that what is the solution of this equation? And if we successfully solve this equation, then we'll get a wave function. Is the wave function concentrated on that particular Glauber-Sudharshan state that give rise to an accelerated solution, or is it concentrated on a different Glauber-Sudharshan? Now, if it all turns out that the wave function actually localizes around those Glauber-Sudharshan state which actually give rise to our universe, that would be a nice success that, okay, nature actually chooses that specific thing. So for that, we need to actually solve this wave function to see that it localizes around a solution out of all these infinite chairs of Glauber-Sudharshan state. It localizes those Glauber-Sudharshan state which give rise to an accelerating universe like ours.
Do we
That
know?
interesting
Sorry,
result.
please go on. Sorry.
Yeah, that's what I wanted to say.
So, do we know all Glauber Sudharshan states?
We have a toy model, of course, and again we analyzed in a toy specific model.
Okay.
But we do know that there are, at least my paper, which I did with my students, we had actually a toy model where we analyzed all possible Glauber Sudharshan state, and we showed that it is annihilated by an emergent Hamiltonian. That part was clear. So that means this is a Wheeler-DeWitt equation for that thing. For a more general M theory case, we don't know all of them. Of course, that's a work. So
I see. Okay. So I have two more questions, about the features of being a physicist, and then I will go to some people's questions. So one question is that, do you have any advice for younger scientists about how to choose what problems to work on?
yeah, I think the way I see it is that being a physicist, you should be able to answer at least some physically relevant question. If somebody asks you, can you answer a question like, if somebody asks you on the road, why is the universe accelerating, or why there are so many standard model degrees of freedom? If you are claiming that you are a physicist, at least we should be able to answer these questions. We can always ask, for our own benefit, we can work on exotic problems like G2 holonomy manifold and all. But will a person who is not into physics, if you make a conversation with that person, and if you say that I'm working on a G2 holonomy manifold, uh, he will not care so much about it.
But there's a physical reason to work on them, right?
Yes, so that if you can convince that person
Yes.
that the physical reason of working, why should we work on, why ultimately we should work on these things? If you can relate it to some physically relevant thing, that's exactly. And so, like people will ask, there is no ADS space, there is no CFT. Why on earth should we actually work on ADS CFT? Because we rarely see a negative cosmological constant space, and we rarely have a scale invariant theory in nature. Why should we spend so much time? The answer is actually quite interesting in the sense that this is the first example where we have a controlled way of understanding quantum gravity, which we never had before. So even though none of these theories are there, there are corners of these theories which are close to real nature. Like, for example, QCD under certain limit behaves like a CFT. We know that for certain choice of coupling constant, there is a small regime of scale invariance there. So we could actually study something like that. And also ADS CFT, we can play around with gauge gravity duality to come very close to infrared of infrared of QCD actually, like the Klebanov-Strassler model. We can come very close to explaining IR of QCD and the confining behavior. An impossible question on one hand can be done in a very simple way on the other side. So we can explain all of these things. So my way is this, my way understanding is that physics should be at least you can explain to your mom what you're doing. Then then that would make sense, I think.
But someone would say that if you are working on an abstract question, you may not know that in the future it may have some practical applications. For example, if somebody is studying something like a 24-dimensional Leech lattice, right? It's very exotic, but we do know that it has practical applications in radio broadcasting. I mean, sphere packing and that kind of stuff. So this is something that someone may say who is studying a very abstract topic. So do you have any counter to
Yes.
that?
So if you can explain this like the way you said this, you tell the person that you are working on leech lattice and all that, and
Yeah.
he will say, "Why on earth are you working on that?" Then you can give an answer to your question that it
But
has a.
at that time, I may not know. It may turn in the future that it has an application, but I may not know
That's
now.
the part you should like. For example, let me give you um, the whole idea of Picard-Lefschetz theory. Why on earth should we care about Picard-Lefschetz theory? It's like exotic theory of mathematics.
Yeah.
It has a beautiful application in to to baby universe and all these things. Now you may
Yeah.
ask why on earth should we care about baby universes and all these things. It turns out that it also has an application. So if you have a universe, our universe, and it spits out a baby universe,
Hmm.
and one of the consequences of baby universe is that it will screw up the coupling of our theory a little bit, in very little way, like electric coupling will change a little bit.
Yeah.
This change is actually captured by Picard-Lefschetz theory. You will not be able to do this thing using standard renormalization group and all this thing. This is
Yes.
captured by a very exotic theory, the Picard-Lefschetz theory. So you see that, but I know how to answer this question. I may not know the answer
Yeah,
to
but Picard and Lifshitz couldn't.
couldn't.
That's the thing.
Now I know the answer to this question. Like at one point, when few years ago, mathematicians were saying, "Oh, I work on Picard-Lefschetz theory," and I was thinking, what would be an application to this one? It's a
Right.
very beautiful theory, and it has an amazing application to physics.
Hmm.
But we may not know. That's the thing that many people will say that, oh, you're working on abstract thing and all. I would say that what you find interesting, and if you can connect it to something real life, I think it will always. Like when I was as a postdoc, I was working on non-killer manifolds and all this thing. People were saying, why you are working on non-killer manifold? I liked it, of course, but then we found a connection to actually uh, real life problem in the sense that because of the moduli stabilization, most of the Calabi-Yaws are not solution. They are actually non-killer manifold become solution. And as you know, moduli stabilization is very important to understand 3+1 dimensional physics. So it
Hmm.
eventually
I mean, there
connected.
was another example where someone may have said to someone like some decades ago that why are you working on elliptic curves? But now elliptic curves are used in cryptography all the time. So
Right.
yeah, you never know.
So yeah, I would say that if you love a subject, go for it. You work on it.
Okay.
It'll all be eventually, if it is consistent mathematically and beautiful, it will eventually be connected to physics, I think, in my opinion.
Hmm. Okay, so another question that I have is that so in your using all of your experience as a researcher, do you have any advice on how to divide your time between multiple projects?
Yeah, so to be honest, I have not been successful be able to do multiple projects at one point. At one point, I can do max 1 to 1.5 actually, because I devote most of my time in analyzing in detail over a specific project. Some people are capable of doing multiple projects over here. Uh, One way I found out to handle multiple projects is that if you can make in your mind a connection between two projects, okay, this is this part of a bigger project, this is that part of a bigger project, then you'll be able to successfully do that multiple project. So,
Okay.
so for example, when I was writing this paper on these heterotic thing, we were also simultaneously working on the Wheeler-DeWitt equations and all this thing. But in my mind, I could connect it because I knew that it's related to Glauber Sudharshan state on both sides, although both paper talk on a very different aspects of the subject. So in my mind, I'm doing a bigger project with one aspect is this, other aspect is that one. So I could do it. If you can make such a connection in your mind, then it's easy for you to go from one to another. That's what I found.
Okay. Okay, so I have some questions from the people. I think you may have answered some of these questions during our discussion, but I will ask you those questions anyway in case you want to add something. So the first question is that can you explain briefly how the proposed deSitter as an excited state compares to proposals such as KKLT and LVS? I think you have answered it, but if you want to add something.
Right. So now KKLT relies on the fact that you have an anti-deSitter space and you add positive energy to this one and you flip the cosmological constant from negative to 0 to positive. Okay, and you get a solution over here. My worry is that this may not be possible in string theory. It may not be possible to flip the sign of the cosmological constant. So what we found was that in our case, we take a 0 cosmological constant solution. And we never got a globally positive cosmological constant solution. What we found is a transient state which seems to have a positive energy. So we could only find that there is a transient state that has a positive energy. And after some time, it becomes Minkowski because it asymptotes to Minkowski. And it's only valid for a limited amount of time. So I feel, I don't have a proof to this statement. I feel that it is impossible to change the sign of a cosmological constant. There's no way to be remaining in an effective field theory. It may not be possible to change the sign of the cosmological constant of the theory. So in KKLT, if you create a coherent state in the KKLT, so there might be a possibility that KKLT would make sense as a GS state, like that. It's a coherent state in anti-deSitter space. So you have an anti-deSitter space, and the whole KKLT construction could be that there is a transient positive energy solution there. Instead of flipping the sign of the cosmological constant and finding a minima of potential, it may be better off that KKLT may be reinterpreted as a transient state the way we have taken.
So wait, so if I understand correctly, when you said that it may not be possible to change the sign of a cosmological constant, you mean, for example, if you do, an uplift using, the second step of KKLT, what you think is that it's not possible?
Imagine I successfully do the uplift. Okay, that means I've got a positive energy minimum.
Yes.
But as soon as I get a positive energy minimum, I told you that if you're not in a static patch, the frequency will change with respect to time.
Okay. Okay. So those
Then
problems come back.
we will not have a well-defined renormalization group flow. So how can you go from a well-defined theory to a regime where there is no well-defined RG flow in the theory?
I see.
So that problem would be there. They did not see this problem because they were always concentrating on static patch. So all the calculations of this were done in a static patch. But static patch is not a good way. It's very deceptive because it's observer dependent patch. So it hides the fact that the system has issues like Transplanckian issues and all these things. That is one of the main reasons why Danielson and other people came up with this, that deSitter does not harbor string theory does not harbor a deSitter minimum.
Okay. Okay, so the next question, it's a bit, I think we did talk about this thing. It's a bit critical, so but the question, I can ask the question anyway. The question is that Ask him that why can't he write like a 10 to 20 page paper that summarizes all the main ideas of his hundreds of pages long papers.
Right. The reason is now we can write it because now that all the results are out, we can write a short
Okay.
paper. The reason is precisely because um, people would have jumped on us. Like, how do you know that Bianchi identities are satisfied in your thing? How do you know equations of motion? How do you know anomalies are cancelled? How do you know flux quantization is done in your setup? Since you are saying that people will say that since you are saying that things are time dependent, how do you know all of these are satisfied? Now, these require a lot of detail to verify because it took us years
Mm-hmm.
to get all of these things out. And I wanted to do this because many people would naturally ask this question like, you cannot, claiming that there exists a time dependent internal space actually creates a vast array of problem. Also, how do you know that these solutions have no late time singularities?
Yeah.
I mean, could it be that at late time they shrink to zero size, have late time singularities and all? So all of these need to be checked before we even claim that there exists a possibility like that.
Mm-hmm. So, but do you plan to write a short paper that summarizes the main
Yes,
ideas?
yes, we are actually working on a
Okay.
shorter paper which explains all. Now that all of these are out, at least no referee would jump on us. Uh,
Sure. I mean, I have to ask because of the number of papers that I've seen which are long. When you say short, what do you mean? What do you mean by
Within
short?
20, 30 page, of course. Within 20,
Okay.
30 page,
Okay.
um, can you express the main ideas of whatever we have? Uh, I believe that's the right way because I believe that if you cannot express, to be honest, uh, I believe that if you cannot express your ideas in 20, 30 page, then you are not yet a good physicist.
Um.
So I write a long paper, but I believe that the answer, the main argument should be explainable in at least 5 to 6 pages. By the time you finish 5, 6 pages, you should be able to know, okay, what's going on there.
Mm-hmm.
Rest is all detail.
Please.
Yeah. Also, we are doing something you will see soon that all my collaborators, at least the student like Archana and Bogdan, they have actually, unbeknownst to me, they actually verified each and every formula. So I told them to write companion papers, which take section by section on put up proof of these things.
I see.
So Archana Maji, who is one of my student, she is putting up a paper soon which verifies section 3 and 4 of this thing, which step it fills up all the intermediate step of these thing, so that anybody who wants to understand. And Bogdan is putting up which verifies section 5 of our paper.
Okay.
And like that, there will be few papers by all my students who will actually provide proof of all of these things in the sense that um, verify that these equations all make sense and fill up the gaps between two lines of an equation. So that if anybody wants to read and if they ever get stuck, they can go back and check, go
Okay.
back and I
Okay.
did the same thing. Yeah, I did the same thing when I was writing a paper on knot theory with Rama. I had a student, her name was Veronica Arastidias. She, again, unbeknownst to me, she verified each and every equation to factors of twos and pi's. So when I found out, I told her to put up this paper, companion paper. So
Um. One question that I have is that when I was talking to Sunil Mukhi, he told me about this story where after Witten's paper on M theory, you and him were working on this paper about orbifolds in M theory, and it turned out that Witten was working on the same thing, and then he cited you. So how was that feeling that a person like Witten appreciated your work? When you were a
right.
PhD student.
So that was, well, first I couldn't believe it, of course. It was my first paper and written. But let me make this clear. I mean, the orbifolds of M theory I wrote with Sunil, but basic idea was Sunil's, of course.
Hmm.
He conceived the ideas. I just verified few details. Let's make this very, very clear. It was Sunil's idea all through from beginning to end.
Right. Right.
Verified few details. So um, I'm just thankful that Sunil gave me a chance to be a part of that co-author. It was, I don't know how Sunil got this idea. It's amazing the way he figured it out. I made sure that all the steps to me make sense. For Sunil, it was obvious. To me, it took me a month to figure out all the detail. So we put up this paper, and then Witten cited this paper. It was first paper, and then getting cited by Witten was too much for her. But yeah, it was a very interesting sensation.
Okay, so I have the last question from the people. It's not about physics, by the way. So it says that what is the best thing about living in Montreal?
Oh, let me clarify that this is something I'm glad you asked. All through
Mm,
my life in USA, I stayed in university town and all. There's nothing around university town. Basically, nothing interesting going on. So Montreal is very different from all other places because right in the downtown, this university is right in downtown.
mhm.
Montreal is a very vibrant city. It's not a very big city, it's a small one. And you can judge it from the fact that you can go to from point A to point B by local transport. You don't even need a car to go. And
Is it a bit like Trieste in, I don't
it's
know, probably.
more vibrant than Trieste, much more
Okay.
vibrant.
But when it comes to size, is it as big as Trieste or is it like bigger?
Slightly bigger, I think, Trieste. Yeah,
Slightly
if I
bigger.
remember.
Okay.
Yeah, I think it's bigger. It's bigger, yeah.
Okay.
Because Montreal has also outskirts and all much bigger
Hmm.
outside. But
I
the
see.
down, but our university is located at downtown, right at the downtown. So and the campus is not very big. Just you go outside the campus and you have restaurants and everywhere, restaurants, movie theater, bookstores, all thing around you. And every pocket of the city it's a city of restaurants. After New York, this is the biggest city with restaurants. I mean, one side you'll have all kind of, there's Indian town, there's a Chinatown, of course. Then there's
Hmm.
Italian town, Korean town, Portuguese town, and also every pocket you go, you get the corresponding foods and all this thing. And very vibrant city. And,
So if you had to pick one good thing that you like the most about Montreal, would you pick restaurants?
and definitely restaurant. The other thing is that it's a mixture of European and American cities. So
Okay.
if you go to, for example, Old Montreal, it look like Venice and uh, places like paved street, and then it has sea and all kind of things and all. And then if you come to downtown, it'll be have big malls and all this thing. You can see the American side of that thing. And then
I
you can
see.
see the mountain, like where I live, just outside my house, I can see the Mount Royal mountain. You can go up the mountain over the weekend and all.
I see. Okay. So I think my questions are over. Thank you so much for your time. It was great to talk to you.
You're welcome.
So if you like this video, give it a thumbs up and consider subscribing, and the YouTube algorithm thinks that you will also like this video.